area bounded by the graph of a continuous function and the x-axis. We want that function to be greater than or equal to 0. The picture I'll draw is going to be strictly greater than 0 in a closed interval. So the graph appears above the x-axis, and we want to fill the area as much as possible underneath the curve with rectangles in a systematic way so that we can have a graphic calculator or some sort of computing utility, calculating utility to crunch the numbers and give us a pretty good approximation of the area underneath the curve. So I actually want to start with the right endpoint approximation, but eventually derive each of these expressions so you kind of get an idea where they're coming from. The picture is going to look like this. We've got a point here A and a point here B. And A is going to be called x sub 0, and B is going to be x sub n. We're going to partition the interval from A to B into subintervals of equal size. Later, we won't require that they be the same size, but equal size, so it doesn't have to be a power of 2. Cutting it up like this kind of makes it looks like it's powers of 2. I just want them to be equal size, and this is the easiest way for me to do it. I'm going to call that x sub 1. I'm going to call that x sub 2, and imagine a whole bunch of little x sub i's in between, x sub k's in between. This is going to be x sub n minus 1, and then eventually x sub n. So the graph could look something like that, and it'll be just from here to there, and we want the area bounded by the curve and the interval from A to B. And we're going to do this using the right endpoint approximation right here. So the right hand endpoint is going to be right there for that interval. So we'd evaluate the function and get this and draw this rectangle like that. We would evaluate it at x sub 2 and get this and draw this rectangle. And it would look like this. Whoa, sorry. Evaluate it at the right here and draw this rectangle. And it looks like this. And then finally at the right hand endpoint there, draw that rectangle. And what we want to do is write an expression for the areas of each of those rectangles, and then use sigma notation to write the sum of the areas of each of those rectangles, and then write an expression for the calculator to find the sum of that sequence of areas. That's what we'll do. Now, the choice of the point in each of the little subintervals is going to change depending on whether it's the right endpoint, left endpoint, or midpoint. So I want to denote what the endpoint is with x, basically x sub k star. So x sub 1 star is the right endpoint of this subinterval, and x sub 2 star is the right hand endpoint of that interval. X sub n minus 1 star, right hand endpoint there, and x sub n star is B, which is the right hand endpoint of that interval on the far right. They correspond with the x sub 1, x sub 2, x sub 3 in this case, but with the midpoint and the left endpoint, they won't exactly correspond with those. So it'll change a little bit. I want to express each of those. Basically, I want to express x sub k star in terms of A, B, little n, however many there are, and the function itself. So let's see, I need x sub k, let's work our way there. X sub 1 star is just x sub 1, so if I wanted to calculate that, I would start at A and basically add the length of one little subinterval. Well, the entire interval from A to B is how long? How far is it from A to B?
B minus A.
B minus A, yeah. B minus A. And if we could divide that length, B minus A, into n equal parts, then each part would be how long? B minus A divided by n. So I need to start at A and go one of those to the right. So it's A plus B minus A over n. That's what x sub 1 star is. So start at A and then scoot one of those little subintervals to the right. X sub 2 star is going to be A plus 2 of them. So start at A and go 2 little subintervals to the right. So 2 times B minus A over N. X sub 3 star, I don't have an X sub 3 star on my picture, but if there were, it would be A plus 3 of them. And the pattern develops very quickly. At the very end, I'm going to leave some space because I'm going to come and put an X sub K star. X sub K star is the one we really need. But I'll leave some space. X sub N star is A plus N times B minus A over N. And we really need that, since that's the right-hand endpoint of the one on the far right, we need that to equal B. Does that equal B? If we divide out the n's and cancel the A and the minus A, that's B, right? Okay, so I need an expression for X sub K star. Well, that's easy. X sub K star equals A plus, well, if it's 1, then there was a 1 there. If it's 2, there's a 2. If there's 3, there's a 3. Ooh, not a tough pattern here. If it's K, then it probably ought to be K times B minus A over N. So basically, I'm just expressing this X coordinate, this endpoint, in terms of A, B, and N, really. Now, we need to evaluate the function there, and that's the height, and then multiply by the width of the little rectangle. So I think we're pretty much in a position to do this. The area of the, how to say this, the rectangle above the interval from X sub K minus 1 to X sub K is, well, it would be the height times the length of that interval. So it's going to be f of X sub K star times B minus A over N, which equals f of X sub K star. This is going to be A plus K times B minus A over N, and then we'll multiply that by B minus A over N. So height of the rectangle times the length of the little subinterval. Length times width, or however you want to say the area of a rectangle. Height of the rectangle times the width, the base of the rectangle. I've left off, no, I haven't, that's it. X sub K star is given by the expression there inside those parentheses. So we've got to evaluate the function there. Now, the sum of the areas of all n rectangles of is spelled OF, right? That was weird. The sum of the areas of all n rectangles is this: sigma K equals 1 to n f of A plus K times B minus A over N times B minus A over N, period. And this is substantially the expression you see right there, except that in that expression, since the B minus A over N doesn't depend on K, it's the same all the way across. I've taken it and moved it in front, or passed it through the sigma notation since there's not a K in it. But it really doesn't matter whether you do or not. I'll probably, for simplicity, just leave it inside there when we type it into the calculator. How do you feel about that expression? Now, what you would need to do then, for different problems would involve different functions, you would need to take that expression and evaluate different functions. I think for simplicity, and something probably you can kind of program your calculator in advance of the test, which should be helpful. For simplicity, you can just type an expression something like this into the calculator and then just go to your y1 equals and change the function. Say if on the review it's the function x squared plus 5x plus 10, you can just type that in. And if on the test it's a different function, all you'd have to change is the function itself, maybe the left and right hand endpoints, and the number of intervals. Each of these things can be changed, but you can kind of have it programmed ahead of time. All I would ask is that you just write down on the test the expression that you typed into the calculator. We'll see what that looks like. It's basically finding the sum of a sequence. I'm going to take this and copy it. Okay. There we go. Copy it over to the next page. And this is going to be a little easier on the TI-83 pluses and the older TI-84 pluses than it will be on the brand spanking new TI-84 pluses. A little bit more of a challenge on the brand spanking new TI-84 pluses, but that's the one I have, so hopefully at least those of you with the newest ones will see what I type in. So if you have the older ones, ultimately you should be able to type something like this. In your Y1, what I'm going to ask that you do is this. X cubed, okay, I don't think we need the key press history, I think is just going to confuse, so I'm going to cover that up. X cubed minus 4x squared plus 30. So x cubed minus 4x squared plus 30. That appears nowhere in the notes. I just kind of made that up an hour or so ago, but it seemed to work fairly nicely. Also, if you want to look at the graph of this, a good viewing window, 0 to 10 for the x-min and x-max, negative 10 to 100 for the y-min and the y-max, and a y-scale of 10 seems to work pretty well. So I would use these as a fairly decent viewing window for this particular one, but you can tweak that a little bit if you feel like it can be improved upon somewhat.
Just the 10 below the origin, so you can still see the graph when the little information bars up.
I'm sorry. Can you say that again, please?
Is the negative 10 in the the y minimum, so that way you can still have it give you the little readout without blocking things.
Yeah, right. And also, just so I can see the x-axis a little bit better. I guess I could set it at 0 and still see the x-axis, but yeah, that's the only reason for that.
Okay, because when you're using calculator, it's got the little.
Right. See the bottom of the screen, the information a little bit better. That's right. Okay. So I'm going to begin with and furthermore, what I want to do is use the right endpoint approximation with n equals 5 rectangles to approximate the area bounded by y equals x cubed minus 4x squared plus 30 and the x-axis between a equals 1 and b equals 6. So each little rectangle will have a base of 1 unit. I don't know that I actually see the picture there, but maybe when we look at the GeoGebra version of it, we will. So from a equals 1 to b equals 6. So if I'm graphing this using the calculator, it'll look something like this. Let's see. There's the picture. So I could shade it. We want to approximate the area from 1 to 1, 2, 3, 4, 5, 6. Really, that's not a good viewing window. I thought I had a decent viewing window of that from 1 to 6. Well, so sorry. I mean, it would work, but maybe I did. Does that fit on the screen? It's close. From 1 to 6, basically we want to approximate that area right there using rectangles. That's what we want. So it's close. You might want to go slightly higher with the Y max, maybe 150 instead. Here's what we want to type. Sum. Now on the calculator, sum, second quit. Sum is going to be on the stat menu. If you've not used this before, you'd press, actually not stat menu, but second stat. Begin by pressing second stat and then press the right arrow 2 times. Stat's right in the middle, and the second button followed by stat, and then the right arrow 2 times to go to the math menu, math submenu of the list, and then it's number 5 down there. So sum to start things off. So we want to find the sum of a sequence. So SEQ is next. Here's where the newer calculators and the older calculators are going to diverge. So I just need to write this out like you would see it on the older one, and then I'll type it in like I have to do on the newer one. So sequence, where's that? Again, second list or second stat. Oh, I'll start back at the beginning, yes.
Where do you get the sum? That thing that you say after?
The sum, it's where it is on the calculator. Again, it's second list on the stat button, and then the right arrow 2 times. Right arrow 2 times to get there. To the math menu, and then it'll be number 5. Right there. The second list sum, and then again second list on the stat button. Just 1 time to the right to the OPS menu at the top, and that will take you to sequence, which is also number 5. And then the different calculators look different. The newer ones look like this, and the older ones don't. So on the older ones, let's see what we need. Basically what we're going to do is try to get the calculator to display y sub 1 of. How to do that? Now you're still on your main screen if you were in the slightly older calculator. I'm going to clear this out, but show you how to do this. You're on your main screen and you press the VARS button. And then you press the right arrow to go to the Y variables. And then you press number 1 to go to function. And then you press number 1 for the Y1. So it's variables, right arrow for Y variables, number 1 for function, and number 1 for Y1. And then open the parentheses like that. Basically, this is f of whatever. So f of, it's going to be a plus. Now for a, all I'm going to vary from application of this problem to the next is the value of n. If you want to be sophisticated with this to prepare for any contingency as you go to take the test, you might want to use the letter a instead of the number 1. Make it as general as possible, but I'm going to go ahead and just go with the number 1 here, because a equals 1, plus, now I'm going to go with k, because k is the index of summation. K is going to go from 1 to 5, because there are 5 little subintervals. K is going to be 1, k is going to be 2, k is going to be 3, so I'm just going to put in the letter k. Now for the letter k, I need to press alpha, followed by, where's the K? It's the left parenthesis right there. So the K. And then an open parenthesis. And let me catch up with myself over here. It's going to be y sub 1 of 1 plus K, and then let me show you what I want this to look like, times B, and it's not B, is it? It's 6 although my b's kind of look like 6's. 6 minus 1, close the parentheses, divided by n. I'm going to go with capital N there. And then close the parentheses, and that's y1 of all that. We're going to evaluate the function at that number, and that's going to give us the height of the rectangle for k equals 1 and for all values of k. That's going to give us the height of the rectangle. So let me type that in. K times 6 minus 1 divided by alpha n. N is on the log button, so alpha log. And I'll close the parentheses there. Come back to this now. Basically, all of this first part is going to be the expression. There's an expression, and we're going to evaluate that expression for k equals 1, evaluate that expression for k equals 2, evaluate that expression for k equals 3, all the way to k equals n, and then stop, and then it'll add them all up. The rest of it I have to multiply by b minus a over n. So I've evaluated, I found the height, now I've got to multiply that by the width of that rectangle. So it's times 6 minus 1 over n. And then I'm just going to put a comma. When I initially did this, I put I mistakenly put a parenthesis after the n, and it turned out I did not need one. Because these parentheses here, I could have accomplished that with just a dot. So multiply by 6 minus 1 over n, that's the width of that rectangle. So when I type it to the calculator, it's going to look like, open parenthesis, 6 minus 1 divided by alpha log, and then a comma right up above the 7, right there. So that's the expression. Now the rest of it is, actually, wait. If you have the newer calculators, sorry, don't type the comma. Newer calculators, delete the comma. You need the comma with the older calculators. Newer calculators, you just tell it the variable. The variable is k. Older calculators, you have to type the k. Well, in both cases, you have to type the k. You just don't need the comma with the newer ones. So the variable is k. That's the index of summation. That's the one that's going from 1 to n. Then another comma. The lower limit is 1. What does the calculator call it? It calls it the start. That's the start. Another comma. Alpha log for n. Calculator calls that the end. I would call it either the upper limit, or I suppose it would be okay simply to call it the end. And finally, the increment. I call it the increment. The calculator calls it the step. And then we can close the parentheses. So the start is 1. It goes from 1 to n, and it increases by 1, increments by 1, steps up 1 each time. And then when I go down here to paste, hopefully it'll paste it all in there, and then the calculators will look alike. Paste. Okay, so if you're using the, please.
Can you slide the calculator over so I can see the rest of the expression?
I can go, just let me know how far to go.
Well, your handwriting is on the
I see what you mean.
Thank you.
Slide the calculator over. That was clear. I don't know why I didn't understand that. There we go. And I can also shrink that down a bit. There. And one more parenthesis probably at the end. I doubt that the calculator will require it, but it won't hurt. because this will give the sequence and then another parenthesis to match the one in between the sum and the sequence there. Now, we have to tell the calculator what n is. N equals 5 in this case. So 5, press the STO button. Take, well, let's see, I'm going to go ahead and press enter. But you probably didn't get 230 if your calculator thinks n is something other than 5. So press enter. See what happens. You get a syntax error.
Can you go in sequence mode and see what is the end and the step? I didn't catch that.
Can I go?
Like, see, what is the start? Start was 1, then the
Yeah,
end.
I got it
Let's see.
and then
Second
step
quit.
and paste.
Well, the start needs to be 1, the end needs to be n, and the step needs to be 1.
Why is the step 1? I'm just curious.
Well, it's the default for sigma notation. Basically, the way sigma notation is defined, we go from the lower limit to upper limit, and we always increase by 1 each time. There may be applications, and we may actually run into an application before we're done, where rather than increasing by 1 each time, it's better to increase by a half each time or by a quarter each time. But the default is 1. In fact, I think with the older calculators, if you leave off the increment, it will be understood to be 1. So what I'm going to do next, I've already pressed enter, and it gave me 230, and it looks like I got to press enter again. It's going to give me 230. I want to make sure that it thinks n equals 5. So I'm going to press 5, and then the STO button. It's got to be short for store. The STO button, and then alpha log. So it stores the value of 5 in the variable n. We've typed n several times. I suppose if you want, you can just change all the n's to 5s. But we store the value of 5 in n, and then redo it in case you got something different from 230, but did not get a syntax error. Second entry. Basically, press second enter a couple of times. Second enter. Until it brings that long sum sequence statement that you typed in and entered in previously. Now, if the calculator thinks that n equals 5, when you press enter, it should give you 230. Did it give anybody 230? If not, maybe it's a good time for me to pause and come around and see if I can see what the issue is. Pause. Because yeah, it'd be good to kind of process it. Process it. So. Yeah, definitely. Yeah, practice it. Practice it many times.
If you put all the tests, that'd be awesome.
Let's look at the GeoGebra, not this one, but let's see. Open. Save it. Why not?
Mr. Meisel, are you going to get all the
I don't think so, but I just tried
expected sections done?
We'll get close. We'll get close. Here is the GeoGebra picture. For f of x equals x cubed minus 4x squared plus 30, you can see that this is probably an overestimate of the actual area with n equals 5 little rectangles, so there's a rectangle for each of the units there. A equals 1 to 6. You can see the shaded region underneath the curve and the rectangles. This one looks like the first couple rectangles because the function's decreasing there. The right endpoint approximation will underestimate the area bounded by the curve and those little subintervals. But once it starts the uptick there, the rectangles will overestimate. So if we add up the areas of those 5 rectangles, it's 230. The actual area, given by calculating a definite integral, 187.08. What if we do more rectangles? Now, hopefully at this point, you've got an expression that's workable. What I would like to think is that you can just take, say, the number 10, type in 10, and store that in the variable n, second log, not second log, alpha log. Alpha log. Take 10, store it in n, and press enter. Now the calculator thinks n equals 10. Now press second enter second entry actually, and then second entry again. Second entry will bring up the 10 store and in, and then if you press second entry again, it'll bring up that entire sum of the sequence expression that you typed with all that stuff. But now the calculator thinks that n equals 10, so when I press enter, it takes just a smidge longer to calculate, and there are more rectangles with n equals 10. The picture looks like that. Oops. I need the calculator and that, and then the calculator again. The picture looks like that, and it gives 207.1875. Still overestimating it, but not by as much. There are more rectangles, and so you can imagine this little portion up here, we're not missing it by that much. This little portion up here, we're not missing it by that much. So it's less of an overestimate in this case. If we want to do 100, you could store that in the value of n, alpha log, enter, and press second entry, and then second entry, and then enter, and it has to calculate the areas of all 100 of those rectangles, and then add them up. And when it adds them up, it gets 188.97, closer to what it looks like is the actual area. The picture, you can see that it's very difficult to see the actual overestimates here on this particular scale. It looks like that ought to be pretty close to what the actual value is.
If you don't have the second entry, like we use our calculator, then you have to go back to sequences and program it every time. Or you can store that somehow. You have to do the whole sequence sum again and just type out the whole equation again.
Well, you could write an actual program and store all that information and execute it, or you type it one time and then after you press enter, then you can do the second enter and it should bring it back up for you.
Or scroll up and click on it with your
If you use a calculator previously, then it's going to be gone and you can really bring it back again from second entry.
Yeah, second entry, I guess.
I'm just wondering, like, if you can go like program it somehow.
Right. Yeah. You know, the process. It's been a long time since I've written a program on one of these. So, but you just kind of have to, jump in there and just imagine what that would be. Yeah. But yes. What?
Or Google it.
Yeah. But that's kind of the idea. All right. That's the right-hand endpoint approximation. Let's see if we can tweak this just a little bit to come up with the left endpoint approximation. Left endpoint approximation. What would change? Well, let's see. I'm going to go back up here and see if I can select a little bit of this. Maybe a lot of it. Maybe all of it. So what if we wanted to do midpoint? Midpoint? No. What did I say? Left endpoint? Left endpoint approximation. What changes? Well, our x sub 1 star is going to be here at the left-hand endpoint of that first interval. And so the rectangle is going to look like that, because that's the number that I use to find the height of the rectangle, the left-hand endpoint. And then x sub 2 star is going to be right there. This is the interval, and I'm using the left-hand endpoint, so it's going to be that rectangle. X sub 3 star is going to be the left-hand endpoint of that interval, so it's going to be that rectangle. X sub, let's see, I have to be careful with this. I suppose technically that should have been my x sub n minus 1 star, because this very last one is going to be my x sub n star. The very last subinterval, we use the left-hand endpoint, and actually because it begins to decrease there, that's actually going to overestimate the interval, whereas the other ones appeared to underestimate the area. So we're looking at that. That's x sub n star. What changes here in the calculations? Well, not too much. X sub 1 star is A. For simplicity and comparison, I'm going to put a 0 there. But the left-hand endpoint of the first interval is A, just where you start. So A plus what? A plus nothing, just A. The second one is x sub 2 star. Well, we start with A and go one little subinterval. So it's going to be A plus one of those. X sub 3 star is going to be A plus two of those. X sub n star is going to be A plus, not all of them, but all but one of them. And so the X sub k star, 1 gives us 0, 2 gives us 1, 3 gives us 2, k gives us k minus 1. So that's why we have a k minus 1 in that expression, whereas we had a k for the right-hand endpoint. That's the only difference. So if you've got your calculator programmed to do the right-hand endpoint approximation with a k, just replace the k by a k minus 1, and that'll give you the left-hand endpoint approximation. I ought to be able to go in and edit that. What would we have here? We would need a k minus 1 right there. K minus 1. We would need a k minus 1 right there. K minus 1. Otherwise, we should be good. I don't think there are any other changes that need to be made to that formula. We just, we're still going from k equals 1 to n, just we're having a k minus 1 in that spot. You think I can edit this and change the k's to k minus 1s? Actually, one of the k's doesn't change, but let's see. Second entry. Let's see. That's just the variable, so that stays a k. This k right here turns into a k minus 1. So I need to insert a parenthesis in front of it, scoot to the right, and then insert a minus 1 on the back side of it, and a parenthesis. Is there another k in the expression, or is that the only one? I think that's the only one. I think it probably would have been equivalent to let k go simply from 0 to n minus 1. That might have been another way to adjust it. But I've got the expression right here. Second. No, I don't want a second. I just want to press enter and see what happens. Enter. Now this is doing for n equals 100 because the calculator still thinks n equals 100. This underestimates it slightly. Let's see if it agrees with what, let's see if GeoGebra agrees with this. What do I want? I want the left endpoint approximation. Yes, 185.221875 if we use left endpoints rather than right endpoints. You might get your calculator to produce this number for you if you were trying to do that. 185.221875. The midpoint approximation seems in most cases to be the one that's closest to the exact value. For the midpoint approximation, let's see what changes. What's still on my clipboard? We can find out. Control V. All of that was still on my clipboard. So if I go midpoint approximation, I need an expression for x sub k star. X sub 1 star, scratch these I guess. X sub 1 star is going to be right here.
So x1 minus a over 2.
I want to say so. This would be a plus half of that. This would be a plus 1.5 of them. like that. X sub 2 star. So if we evaluate it right there, the top of the rectangle looks like that. Here, the top of the rectangle looks like that, and I suppose I should erase these other pieces of rectangles. Oops, not the curve. Not the curve itself, but just the other pieces of rectangles. So it looks like that. The midpoint is there, and the midpoint is there. So x sub, this would be x sub n minus 1 star, and then x right there, x sub n star. So how do I write that in terms of k? I think you had it, Patrick. What did you say in terms of k?
Well, for each one xk minus, well, for x1 I had x1 minus a over 2.
Yeah, maybe there's a better way I could write it. The fractions are going to be more difficult to work with. Plus, 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 plus. Yeah, I'd like to say k minus 1/2. That may be what you said. This would be 1 minus 1/2 equals 1/2, doesn't it? Yes. 2 minus 1/2 equals 3/2. 3 minus 1/2 would work there, and the last one would be n minus 1/2. But the one that we care about is the k minus 1/2. So if I could go in here, second entry, and change the k to a k minus 1/2 right there, change that 1 to a 1/2, this should give us the midpoint approximation. So 1 second, I want to be on the other side of it, just beyond the 1. Second insert divided by 2, and then press the right arrow. This should give us the midpoint approximation, which should be a really close one. For 100 rectangles, let's see if this compares favorably with what GeoGebra gets.
With rounding, it's pretty much the same.
Yeah, 187.0765625. That's what we have there, and very, very close compared to the left endpoint approximation and right endpoint approximation. So the midpoint approximation seems like a more efficient way to do it. You would need lots more rectangles if we wanted to get that close to the actual value. We would need a lot more for the left endpoint or for the right endpoint approximation.
It seems like the best thing to do might be to get the average of all three.
The average of the left, right, and middle. I'm wondering if in a lot of cases the midpoint itself might be I wouldn't say it would necessarily be exactly the average of the left and right. I should think about that.
Yeah.
But the midpoint tends to be closest for most of the functions that we'll be concerning ourselves with.
Or I wonder if the midpoint is just about the average of the left and right.
It's probably not far away from it. Okay. And that's plenty of that. Section 5.3, I know you're worried, but 5.3, except for some basic definitions, I'm not going to trouble you with the actual. Wait, sorry. 5.2. Basically, everything that I want to say from 5.2 has been said. There are some ways of writing this so that it is not necessary to use the calculator, but I'm not going to ask you to do the example like this that requires the formulas for sigma, k equals 1 to n, or of k, or k squared, or k cubed. So These particular examples here are here for your viewing pleasure, for your edification, but do not expect something on the test where I ask you to come up with an expression like this in terms of n. I'm going to be looking for you to use the calculator with the f of x, y, 1 of x notation, and not like one of these. So I'm going to go directly to section 5.3 after a short break.
Mid.
What company?
All right, I think we are just about on back, if not completely on back. 5.3 beginning generalizes the idea that we've been looking at for calculating the area under a curve into that of a Riemann sum. We're going to relax some things just a little bit. Going to keep with the theme of a closed interval from A to B. Keep with the theme of a continuous function defined on that closed interval. What's going to be different is that instead of having intervals, little subintervals of equal width, all b minus a over n, they'll vary. Just imagine a partition where x sub 1 is right there, of course x sub 0 is right there, and x sub n is right there, but maybe x sub 2 is way over there. And then x sub 3 is real close, and x sub 4 is even closer, and x sub 5 is like that, and then we're to x sub n. Just kind of a, I won't say random, although it did seem like that, yes.
I forget, is the extra credit due by 3 or just by the end of the day?
By the end of the day, I mean, it could be
Doesn't have
late
trouble
into
getting
the evening if it needs to be.
Because I'm having trouble getting the variable.
Yeah. Yeah, late into the evening if necessary. In each of these little subintervals, the idea is we're going to pick some x sub k star. It doesn't have to be the right-hand endpoint consistently across the board. It doesn't have to be the left-hand endpoint or the midpoint. It can be anything in that subinterval. So pick an x sub 1 star, and maybe I should color that a different color. X sub 1 star, and evaluate the function there, and get a point on the graph. Pick maybe an x sub 2 star, and evaluate the function there, get a point on the graph. And let's see, we need an x sub 3 star right there. I did too many of these. X sub 4 star, need a point on the graph. X sub 4 star, point on the graph. X sub 5 star, x sub 5 star, point on the graph. And finally, an x sub n star. Let's say right there, x sub n star. Not necessarily at the midpoint or the left endpoint or the right hand endpoint, somewhere in between the endpoints of the subinterval, we choose those x sub, in this case I'll say x sub I stars, and we get rectangles. Rectangle there, and a big rectangle there, goes all the way across like that, and not so big rectangle there, and kind of a skinny rectangle right there, and then a bigger one there. And finally, where was that point? Right there. Like that. So, several rectangles. Calculate the sum of the areas of all those rectangles, and hopefully that's kind of close to the total area bounded by the curve and the x-axis. How could we make it closer? Get more rectangles. Get more rectangles. Now, more rectangles for sure, with one additional provision. So more rectangles ought to make it closer, but what we would like, basically, this is f of, and I put x's, and in my formula I have c's. Is that what you were laughing at, Jesse?
Yes.
All right. And I don't even have stars, by the way. I'm going to leave the stars just because. C sub 1, C sub 2, C sub 3, C sub 4, C sub 5, C sub n. We evaluate the function, find the height of the rectangle, f of C sub I. We say delta x sub I is the difference between x sub I and x sub I minus 1. So we multiply by delta x sub I, and we add them up from I equals 1 to n. We want the area to be closer. So we do more rectangles, so n should approach infinity for sure. But there's one other consideration that has to be made. Not only does n have to approach infinity, but consider this. Suppose when we make more rectangles, what we do is we take this rectangle and we just subdivide it like crazy, like that. And I guess what happens is it has the effect, and we just put thousands and thousands of rectangles right in there, but, and that drives into infinity, but it doesn't have any effect on the rest of the subintervals. And we could even maybe take another one and subdivide that into a whole bunch of rectangles like that. But in addition to letting n go to infinity, the length of the largest one, basically this partition is called delta, and we denote the norm of the partition by what looks like double absolute values symbols, and what it means is that the norm needs to approach 0 in order for us to ensure that this is going to be closer and closer and as close as we need it to be to the actual area bounded by the curve. So n is going to have to approach infinity. If the length of the largest subinterval goes to 0, we're necessarily going to have an arbitrarily large number of rectangles, but we want to make sure that we don't allow for the possibility that one rectangle could just have a really great big width, because we're always going to be off by that much. So the widths of the rectangles have to shrink as the number of rectangles approach infinity. And basically the summary of it is that. So we don't have to say n goes to infinity. All we have to do is say that the norm, basically the length of the largest little subinterval, approaches 0 over all possible partitions that one could make there. If that limit exists, then f is said to be integrable on the closed interval AB, and the limit is denoted by the definite integral. Don't know why I didn't put it in boldface type. That's an extremely important term there. The definite integral of f from a to b. And whereas previously we've used that to denote the antiderivative, in this case it kind of denotes something else. We're going to be able to use antiderivatives to calculate it in a lot of cases, but it represents the value of this limit, which for us, best way we can interpret this, is the area bounded by the curve and the x-axis. So we're going to denote this area like this. We have a theorem. I'm not going to prove the theorem, but we have a theorem. If a function is continuous on the closed interval, then it is integrable on that closed interval. What it means for us is that if we have a continuous function, there's a and there's b, then that area is defined to be this limit, and it's actually well defined. There are ways to define functions that are not continuous on an interval like that in really bizarre kind of ways. Well, it doesn't have to get that bizarre. We could mix in a vertical asymptote or something like that and cause this limit not to exist. But if the function's continuous on the closed interval, we're guaranteed that the limit will exist so that the area bounded by the curve and the x-axis is, in fact, well defined. Some properties. Let's see if this makes sense. If I'm going to go back to this picture, if this is the integral from a to b of f of x dx, What do you suppose is meant by the integral from b to a of f of x dx? It's going to make a difference which endpoint we put where? Well, it turns out that it's a simple transition from one to the other. It actually is a well-defined expression because we might have a need when we do integration by substitution. Sometimes we'll run into integrals where the lower limit is a greater number than the upper limit, and what we do to fix that is we reverse them and adjust by multiplying by -1. We'll have a theorem down below that will tell us that if the lower limit is actually the greater value and the upper limit is the lesser value, this and this are opposites of each other. This equals the negative of that. Oops. Grab the A and the B there. So let's look at this picture and see if this makes sense. Suppose we have an A and a B as the endpoints of the interval, and the curve looks something like this. I'm going to put a C in here somewhere. How about right there? I'm going to call this region 1 and call this region 2. If we write the integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from c to b of f of x dx, does this look like it ought to be true? What region, what area is represented by the integral from a to c of f of x dx? This is region 1. And the integral from c to b, that's got to be region 2. And if we look at the integral from a to b, that's the sum of those two areas. So that would be 1 plus 2. So it seems to work nicely in that case. But then it says, regardless of how a, b, and c are ordered. So there are 5 other permutations of a, b, and c, putting them in order from left to right, that we haven't considered. Let's consider 1 or 2 others. What if I take the c and put it there, and the b and put it there? Erase. Now what do we mean by the integral from a to c? Then the entire thing, 1 plus 2. What do we mean by the integral from c to b? Now it's backwards because c is the number on the right. It's the right-hand endpoint, but it's the lower limit. And b is the left-hand endpoint, but it's the upper limit. So this is actually the opposite of the integral from b to c. So this would be the negative of region 2. If we go from b to c, that would be region 2. But if we go to from c to b, that's backwards. That would be the negative of region 2. That would give us a negative number as our answer, basically. And from a to b, that's region 1. And I think if we simplify, cancel the 2's, 2 and the -2, then we get 1 equals 1 on both sides. So it works there. You can scramble the a, b, and c 4 other different ways, the other 4 permutations that we haven't done, and see if it makes sense. But basically, you kind of need the fact that this fact right here, if you reverse the limits of integration, it has the effect of multiplying the answer by -1. And we'll see that below, but I needed to go ahead and mention it there for that particular theorem. Example 2. basically we just want to use familiar formulas from geometry to evaluate these integrals. We could also use calculus to evaluate the integrals. We just haven't learned how to do that yet. So we're going to use each of these integrals as something that represents the area bounded by a continuous function and the x-axis, and calculate the area. Let's see what we have. So the picture from 0 to 3, 3 minus x, 1, 2, 3. So 3 minus 0 is 3. 3 minus 1 is 2. 3 minus 2 is 1. 3 minus 0 is, 3 minus 3 is 0. So this graph looks like that. Would this pass for the graph of y equals 3 minus x, you think? Does that look okay? So between 0 and 3, we want the area bounded by that curve and the x-axis. It's a triangle. What's the formula for the area of a triangle? 1/2 base times height. So I'm going to say 9 halves, 4.5. So this equals 4.5. Simply thinking of it in terms of the area bounded by the curve, not a particularly curvy curve, but a curve nonetheless, and the x-axis. 4.5. If I did the arithmetic correctly, that's the area of that triangle. What about this one? I think this one is a rectangle for sure. It may even be a square. 1, 2, 3, 4. 1, 2, 3. So when x equals 1, it's 3. When x equals 2, it's 3. When x equals 3, it's 3. When x equals 4, it's 3. It's constant. It's always 3. So the graph is a horizontal line segment. And if we go like this, it is a square. The base is 3. The height is 3.
Isn't base? Yeah, it's 3.
Yeah, from 1 to 4.
Zero indexing.
Yeah, from 1 to 4. So 3 units there. So it's 3 times 3, which is 9. So the value of this definite integral is 9. Just the connection here. Definite integral, area bounded by the curve and the x-axis. So we're just using a formula from geometry, length times width, or side squared, I guess. Now, then all of a sudden it gets weird. This problem, the C part, almost always shows up on the last exam or on the final exam, maybe both, and it doesn't go as well as I think it ought to go. What is this the graph of?
Circle.
It is a circle. Y squared equals 4 minus x minus 3 quantity squared. Well, it's the top half of the circle. It's semicircle. So add the x minus 3 quantity squared to both sides. X minus 3 quantity squared plus y squared equals 4. And you can compare this to x minus h quantity squared plus y minus k quantity squared equals r squared. So it's a circle whose center is the point 3, 0, and radius length is 2. So we need the top half of that circle. So 1, 2, 3, 4, 5. So if the center is the point 3, 0, go 2 units to the right of that, and 2 units to the left of that, and 2 units above that, and draw a semicircle. The graph goes from 1 to 5, conveniently. If it had been from 1 to 4, we'd have had trouble doing this. We'd have a piece of the circle missing, a vertical slice. From 1 to 3, I think we could have done that because it would have been a quarter of the circle. And we could divide pi r squared by 4. Here we have to divide pi r squared by 2 because it's the area of this semicircle, like this. So area is going to be 1/2 pi times the radius squared.
Is it half circle?
Is a half circle. So the area is 1/2 of 4 pi. It's 2 pi. Now, to check yourself, your calculator will do some basic calculations of definite integrals if it's not too terribly challenging. If you graph y equals 3 minus x, I guess I should go back to a standard viewing window. Zoom 6, 3 minus x, zoom 6. Looks like that. If you press the second button, followed by the trace button, the calculate menu is where we want to go. Number 7 on the list has the integral symbol. It'll calculate a definite integral. If we go down to 7, there we go. It will ask for the lower limit, that's 0. Then it will ask for the upper limit, and that's 3. And it'll even shade it for us and calculate that that area is 4.5. If we change it to y equals 3, horizontal line, but we just want to tell it to find the area between 1 and 4. Second, calc 7. Lower limit is 1. Upper limit is 4. And so, in this viewing window, it doesn't look like a square, but it's a square. That has an area of 9. And then the circle, if we go, let's see, I guess second quit, y equals the square root, second square root of 4 minus x minus 3 to the second power. And if we calculate it as radicals and exponents a little differently from this one, don't sweat it because you can type that in, it's just a matter of figuring out how. Let's see if it looks at least like a semi-ellipse when I graph it. Graph. There we go. Kind of looks like a semi-ellipse something. Second, calc 7. If we go from 1 to 5, it should be 6.28 something. There we go. So about 2 pi. There we go. So in a lot of cases, the calculator can help you to confirm the suspected value of a definite integral. Sample 3, a little different, because for the first one that we've looked at, a portion of the graph is below the x-axis. For this one, 0, 1, 2. 2 times 0 is 0, minus 1 is negative 1. 2 times 1 is 2, minus 1 is 1. And 2 times 2 is 4. 4 minus 1 is 3. So 1 up there somewhere. Now the way the definite integral is defined, it respects whether a function has a positive value or a negative value. If we're thinking of it in terms of area bounded by a curve and the x-axis, if the graph is going to be above the x-axis, that area counts as positive. If a portion of the graph is below the x-axis, that area counts as negative. So what we're not calculating is the total area bounded by the curve and the x-axis. What we're calculating is the net signed area. Net signed area. So if a portion of the graph is below the x-axis, what I would have to do is calculate this area 1/2, and it looks like base times height, and that's going to be 1/4. So 1/4 in there. And then also calculate this. That looks like 1/2, 3/2 times 1, 2, 3. 1/2 base times height. So that's 9/4. The total area bounded by the curve in the x-axis looks like it's 1/4 plus 9/4, which is 10/4. But the value of the definite integral, the 9/4 makes a positive contribution. The 1/4 makes a negative contribution. So it's actually 8/4 or 2. And I think your calculator will agree with that. Let's see. Y equals 2x minus 1. Graph it. Second, calc 7. Lower limit 0. Upper limit 2.
Excuse me, sir, I need to leave.
Oh, all right. And it's 2. So it's the net side area rather than the total area bounded by the curve and the x-axis. The area is above the x-axis makes a positive contribution. Area below the x-axis makes a negative contribution. So there'll be situations where we might need the net signed area. Other times we might need the total area, and we want to make sure that we're clear on the difference between. The next one's going to end up not being defined, but I don't think there's time to talk about that now. Or wait, maybe it is defined.